The beginning of mathematics starts with numbers and counting, which at one time humans did not know anything about. One of the age-old questions actually is, did we invent numbers or were they already there? Now, of course, we use a 10-digit number system, but there's no mathematical reason for that. There's no reason we could not have 9 digits, which means after 8, the next number would be 10 because you'd be out of digits and you would need to reset the ones place to 0 and then add a 1. This would represent what we know of as 9 if there were 9 digits. We believe that the 10 digits comes from the fact that we have 10 fingers. Simple as that. In fact, there are many times we only use 2 digits. It's known as binary. But mathematicians actually say had we picked 12 digits, then arithmetic would be much easier considering 12 is divisible by more numbers than 10. Now, one of the oldest foundations of mathematics, which is lost on many people today, is logic. Although a lot of advancements in this field were done in the 19th and 20th century, it started around 2,500 years ago. In a logic class nowadays, you'll notice some odd examples of problems that involve just thinking. For example, take the sentence, if it is raining, then the ground is wet. Let's say that is definitely a true statement. Now, is this next statement also true? If the ground is not wet, then it is not raining. Anyone who's learned basic logic, which even includes various geometry students, can answer this in a second. Others may need a little more time, but these two statements are in fact logically the same. In fact, whenever you say if something, then something else, it is always the same as saying if not the second thing, then not the first thing. If an angle is 40 degrees, then it is acute, and if an angle is not acute, then it is not 40 degrees, are logically the same thing. Concepts like this may seem weird, but within mathematics, we need very formal language that we all agree on in order to prove theorems that are extremely difficult to understand. If you were asked to prove the statement, if x squared is even, then x is even, you now know you could also prove if x is not even, then x squared is not even. Proving one automatically proves the other, and although this is an easy example, when dealing with more advanced mathematics, we need a very clear understanding of the language and logic behind every statement. Then a little later, just over 2,000 years ago, the mathematician Euclid published a series of 13 books known as Elements, which many regard as the most influential textbook of all time. While there's a lot discussed in these books, one important concept is the Euclidean algorithm or Euclid's algorithm, one of the first mathematical algorithms ever discovered. An algorithm is simply a series of steps that solves a problem, executed often but not always by a computer. This algorithm calculates the greatest common divisor of two numbers in an efficient way. So if you want to know the largest number that goes into, let's say, 714 and 1054, it would not be that hard, but may take a little bit of time to find the answer is 34. Instead, we can use the algorithm. I'm not going to explain how it works, but just involves basic elementary school arithmetic, and usually you can probably figure out the answer by hand in less than a minute. I mentioned the algorithm because it extends the field of cryptography. Cryptography is really about techniques that ensure secure communication, especially in the presence of adversaries such as hackers. When putting sensitive information online, let's say, no text is encrypted using mathematical techniques that turn the text cannot be understood by a third party or anyone. I think we're different back to original text, which is easy to do, or the two parties are.
numbers and 0 is countable. Now that does not mean that you can count every element in the set. It does go on forever and therefore is an infinite set.
But it is countable.
Well, actually countably infinite.
And that's because I can order all the elements such that nothing ever repeats, and I don't skip them. Is the set of rational numbers countable? Rational numbers are either decimals that end or decimals that go on forever but repeat. 2, 2.2, 2.34 repeating, 2.594, etc. These are all rational. Now, can I line these up such that I have a first rational number, a second, a third, and so on, such that I don't skip anything? Amazingly, it was proved that the answer is yes. The set is countably infinite. First, remember that any rational number can be expressed as a ratio of two integers. Now, the most classic proof is ordering the rational numbers in a clever way such that they are in this form. You have rows and columns of integers, and every entry is the ratio of those two numbers. We can start at the top left corner where 1 is our first rational number. Then we go down to the next for the second, then diagonal, and keep going while skipping the rational numbers that repeat. Doing this, we would eventually reach any rational number you could pick. Even this repeating decimal and therefore rational number is just 67 over 241. And if you continued this pattern forever, you'd eventually find that 67 and 241 column and row. If you study math or maybe computer science in college, you will learn how the set of irrational numbers is actually not countable. There's no way to line them up such that you list every single one without skipping. This means you could say that there are more irrational numbers than rational, even though there are an infinite amount of each. You'd also see that the set of real numbers, which includes integers, decimals, pi, square root of 2, etc., is also not countable. Set theory now has applications in several topics we talked about, including graph theory, topology, group theory, and more. Now, when you flip a coin or play a game of roulette, every single event is an independent one. It does not matter what your last spin was, the odds of getting red on this next one are still the exact same as before. Well, in the early 1900s, work was done on a statistical model describing events in which probability depends only on the previous event. This model became known as a Markov chain. Markov chains include a state space and transition probabilities. Imagine you want to analyze the population of Los Angeles and New York. For simplicity, we can say people only can move from one to another, or they can stay put. So maybe every year 10% of people who live in LA move to New York, meaning that 90% of the people stay. And at the same time every year 15% of people in New York move to LA, meaning 85% stay. In this example, where you are now matters. Based on if you're in LA or New York, we can predict whether a person may move or not.
But saying that a person took this specific series of moves really does not matter in terms of what comes next. Using certain techniques, in this case linear algebra, you can determine how the system will evolve over time and whether it will reach some steady state or not. These apply to thermodynamics and representing certain unknown details of a system. They apply to modern speech recognition systems, and they are what defines the page rank of a website as used by Google. Then also in the early 1900s, work was being done on the existence of a strategy in two-person zero-sum games, or games in which one person's gain is balanced out by another's loss. This field, started by John von Neumann in 1928, became known as game theory and quickly expanded throughout the mid-1900s. To summarize, it's about the study of logical decision-making and strategy within competitive situations. One of the most famous, quote, games that came up in the early days of this field was the prisoner's dilemma, where you and a co-conspirator have been imprisoned for committing a crime. You're separated and each have the option to either stay silent or rat on the other and say they did it. And based on what each of you do, you may go to jail for a certain amount of time or you may be set free. The question here is, what is in your best interest to do, especially while not knowing what the other person will say? This field grew to have applications in both economics and computer science, as well as a few other fields. In computer science, there's cloud computing, in which game theory can be used for modeling interactions between cloud providers where costs should be minimized while other factors maximized. In economics, it applies to auctions, mergers and acquisitions where each party wants the most benefit, financial analysis and a new product release, and much more. Then in the 1880s, the mathematician Henri Poincaré was studying the three-body problem, which deals with studying the motion of 3 point masses. For example, the motion of the moon, earth, and sun under each other's gravitational pull. Analyzing the motion of two orbiting bodies is very doable using Newton's laws of motion. But throw a third in and it actually gets very difficult. Now, Poincaré found that small changes in the position and initial velocity of these masses would cause for way different behaviors over time. This was the beginning of chaos theory, a field of math dealing with dynamic systems that are very sensitive to initial conditions. Now, after his contributions, the field slowed down a lot due to the lack of computational power back then. Eventually, a man named Edward Lorenz accidentally found his interest in this subject through his work in weather prediction in the early 60s. He realized that when he made a small change to initial conditions in his computer simulation, it produced huge changes in the long-term final outcome. You may have heard of the butterfly effect, a metaphorical example where if a butterfly flaps its wings on one side of the Atlantic Ocean, let's say, it could cause a tornado on the other side weeks later. Well, this very minor change in the environmental conditions causing a large difference is a concept of chaos theory, and its name, the butterfly effect, was coined by that man, Edward Lorenz, after his findings with the weather simulation. Now we can use chaos theory to analyze systems like a double pendulum, where changing its starting height even a little greatly changes its path. It's used in robotics to predict the motion of a robot and how it will develop over time, and it can even be used in cryptography. Next up, geodesics are curves representing the shortest path between 2 points on a curved surface. These are what an ant living on the surface would perceive to be straight, and it explains why airplane routes on a map are curved a little. These are of huge importance for Einstein's general theory of relativity. Moving on, Fermat's last theorem, which is easy to understand on the surface, was unsolved for 300 years. This theorem says that there are no three integers a, b, and c such that this is true, where n is any integer greater than 2. No one could prove whether this was true until just a few decades ago in 1994, where Andrew Wiles finally proved the theorem and found that in fact there are no integers that make this true. And although the theorem is easy to understand, the proof involves very rigorous math taking up over 100 pages. And last is the Millennium Prize problems, which are 7 very difficult problems within mathematics. These 7 were decided on at a conference about 2 decades ago, and each question comes with a $1 million prize if you solve it. But so far only one of the 7 has been solved, which was